Okay, the CCT diagram of eutectic stainless steel. This is the last topic where we stop. Okay, it just gives a various transformation product which will be obtained at different cooling rates. At the end, our product are usually martensite or perlite depending on the cooling media. Okay, so this one, uh, okay, the hardenability is this quench and method is a process where we determine the hardenability. Okay, the hardenability that's basically it depends on several factors. Okay, number one is the carbon content. Okay, remember what will happen if the carbon is low. What will happen if you're still having very low carbon content? What will happen if you do the quenching process? Anyone? Can you hear me?
Yes, sir.
Towards the hardness. Okay, what will happen in terms of the hardness?
That time, but not so hard.
Not so hard. Okay, it will be that time. Why? In fact, we already quench it. It's experienced fast cooling. Okay, will it increase the strength? Quench is means fast cooling. Okay, if we heat it up and cool it very fast, what we can do? Yes, of course, we can increase the strength, but not as maximum as the formation of martensite. What we obtain is a grain refinement only, grain refinement effect. Okay, the size of grain will reduce compared to maybe previously it's not as finer as before. But grain refinement effect you can obtain. For example, if originally it's contained coarse perlite, it will become fine perlite. Okay, fine perlite. That's it. It increases strength, but very limited. If you use high carbon steel, okay, for high carbon steel, okay, we don't talk about the grain refinement anymore. We don't talk about this, okay, because it's totally changed perlite into martensite. What happened is you change perlite into martensite, and the martensite, of course, is stronger than fine perlite. So that's the reason you need to know at what limit you want to achieve. If you think of very hard properties, of course, you need to know what is the value of hardness for martensite. Okay, this value can be an indicator for a comparison, a qualitative analysis. Okay, so you jangan berangan lah nak capai very super hard by using low carbon steel because there's no way you can form martensite. So you need to know what design requirement. Okay, so if you look at these different types of alloy, okay, the alloy actually influence the hardenability. Okay, how the hardenability can be interpreted from here. Okay, if you look at here, okay, the distance from 0 to far from the quench end, okay, 32. This alloy shows the highest hardenability. Why? Because even though the distance far from the quench, meaning that it is the compared to the others, this one is the slowest. I mean that I can say it is slowest, meaning that even though the position of the specimen, let's say this is the specimen, okay, you do the quench here, right? Okay, this point will be the first point where forming martensite. Okay, uh, the first point where cool it rapidly once you inject with the water jet. Okay, so meaning that from this point to this point, it can experience fast cooling or experience the metal subformation, either one. Okay, so the ability to achieve this hardness value, okay, at the point far from the quench ends, showing that this alloy highest hardenability. Okay, so you don't worry if you have a large component size. Okay, for example, your product is very huge, large. So if you want to improve the hardness through the quenching process, you don't worry that the inner side, the core level of the material will not experience a quenching effect. You don't worry because it is high hardenability. Even though the size of the component is huge, but still it can achieve the hardness level that you want at the core level. Okay, for example, your material is very big compared to the small one, it's okay. You don't worry because it will cool it very fast. But the huge dimension of the product, you do the quenching immediately, the core level will experience the quenching effect. So you need, for large component, you need to use high hardenability material if you think you need to achieve this value of hardness. Okay, look at the dimension, 32 mm. It's not so it's not so thick. It is about 3 centimeter. So if you have a metal plate that having 30 mm, okay, 3 centimeter plate, it's very thick plate. You want to harden the material, make sure you use this alloy, okay, because you know once you do the hardenability process at the core level can achieve the hardness larger than 35 hardness rock well value. Ibu ada kelas, ibu ada kelas. Ya.
Ibu lukis salah, ketam. Ketam airnya lukis besar.
Okay.
Salah.
Alright, sorry, yeah. Okay, so this is the application. So you have this chart. You look at which performance of your alloy, you know. Okay, so if this trend shows in the profile of your material part, so meaning that you can ensure this can be hardened when you conduct the process. Okay, you cannot just simply do a quenching and whatever treatment process without knowing this. Otherwise, you just wasting your time. Okay, you do the heat treatment process, but you don't know whether it is improved or not. You don't know what is parameter you need to optimize. What is parameter you need to set. Okay, without this knowledge. So you must understand this. Okay, carbon content, alloying elements. Okay, austenitic grain size. So this part is really influence the final product. Okay. So the CCT diagram of this alloy is different to iterated alloy, the plain iterated alloy. Okay. So if you look at the CCT alloy, okay, CCT 4340 steel alloy. All right. The phase transformation. Okay. Phase transformation, the curve. The time 200. Okay, even though you delay the time, okay, you know that you can obtain 100% martensite even though the time is 50 seconds or almost 1 minute. You delay the time, you can get 100% martensite. Okay, if you delay more than that, you can have a different portion of martensite. See, this curve is this curve for CCT diagram. Okay, for this kind of alloy, different with iterated alloy, iterated steel alloy, different. Okay, if you compare for iterated alloy, you need to perform this whatever process to obtain martensite plus return austenite at 1 or 2 seconds. Okay, not more than 5 seconds. But this one, 50 seconds. Look at this, 50 seconds. 50 seconds. You can delay up until 50 seconds and you can ensure you can obtain 100% martensite. So hardenability is high. Look at this curve. Okay. So the application rotating shaft are frequently subjected to friction. Okay, this component. So friction, we know about friction. You need to know that the surface will experience wear phenomena. Wear phenomena. So it's require hard surface due to the friction. We want to avoid wear. We need to provide hard surface. Okay, this is very typical concept. Just now, the class I conducted at 2 p.m. just now, it's about surface engineering. Okay, and focusing on enhance the surface only, because we know there are so many rotating equipment that experience wear phenomena because of the friction. So the treatment on the surface is critical. Okay, the selection of the best material itself is critical, but optimum the design by modifying the surface also really important. Another chapter, another area, okay, for improvement the properties for this particular application. Okay, so we require high hardness for the surface of the shaft. Okay, so we use the CCT diagram. We could predict at what time. Okay, we can formulate the heat treatment procedure to transform the surface to shaft into martensite while maintaining the core duct time. So we need to know how many percentage that martensite, or maybe you don't need full martensite. So you can always modify this. You need to always to refer this CCT diagram to determine which cooling time that's suitable for your application. Is it 100% or is it martensite plus perlite? So it depends, because different microstructure will produce different properties. Okay. Are you still there?
Yes, Doctor.
Okay. Boleh tak keluar sebab saya ni. Okay. All right. Okay, so the micrograph of perlite and martensite at the core and surface respectively. Okay, so this is the core, this is the surface. You can get differently, right? Meaning that you conduct this martensite plus perlite, okay, and what you get is the mixture, okay, the mixture transformation only on the surface. Okay, only on the surface, because whatever you obtain, the total materials, okay, meaning that this is your component. At this point, your component shows a perlite formation. Okay, inside the austenite. This is austenite. This is perlite. Okay, perhaps it's formed at the let's say the boundary. Okay, like this. Okay, so you got this at this point. It's transformed into perlite, and then going out from this curve, going out from the CCT curve, what happened is they are going to martensite. these are the area of martensite. Okay, so who will change into martensite? Only austenite can change into martensite. So what happened is these are martensite. Where martensite will form on the austenite. Whatever you obtain perlite will remain as a perlite. Okay, so the perlite, okay, the total perlite formation, okay, is not complete. So what happened is on the surface dominated by martensite, okay, dominated by martensite because it will cool it first, okay, and the rest will be perlite. Okay, perlite core, martensite shell. All right, cooling rates differ for different bar diameter for different position in the cross section of the specimen. Okay, for the quenching media. Okay, for example, like okay, just a second. Okay, the media is a water and the oil. Okay, water and oil. So the cooling curve rate is different. Okay, the cooling curve for okay, the cooling curve bar diameter. Okay, the increase in diameter, the cooling rate will be different. Okay, smaller will be this part is quite confusing. Cooling rate at 700 BC. Oh, okay, sorry. All right, this cooling rate, 700 degrees Celsius per second, experienced by, represented by this point. For example, this 700 degrees Celsius for 60 diameter, experienced at the distance of this distance. Okay, but for the no, this is not. Tak, I pun tak faham nak graf ni. Mesti terbalik je. Larger 80 will be farther. Nantilah I explain. Okay, I tanya orang yang buat ni dulu. Alright. Okay, the quenching media, of course, is experience different cooling rate. For example, air or compressed air, slowest cooling rate. Still, we consider quenching, depends on the size. Okay, sometimes large size will not experience a total quenching effect if you cool it at the in the air. Oil is a moderate cooling rate. Okay, but it's more rapidly compared to the air. All right. For the water, okay, it cools rapidly. Okay, more rapidly compared to oil, and brine is a mixture of salt and water, and it is produce the fastest cooling rate. All right. Okay, in summary, to select a steel from a component that will be heat treated, it is important to know its hardenability. Means that you cannot just straight away conduct the heat treatment without knowing that whether or not it is can be hardened or not. Okay, for example, you do quenching for low carbon steel. Okay, you expect that it form martensite, but actually it is only minimum amount of martensite because the carbon is very small, not small, low. Okay. Then what else? Jomini and quench test is used to determine the hardenability of metals. CCT diagram is constructed using a data obtained from the Jomini and quench test. The treatment procedure for steel can be formulated using CCT diagram to obtain the desired microstructure. Okay, that's all for the heat treatment process for the steel. Any question?
No, Doctor.
Okay. So if no, we move to the next lecture notes. Okay. Which is we will move to the next topic called cast iron. Okay, cast iron.
Lampu. Lampu. Okay. Itu untuk membuat kan. Jadi kalau Agi ada Agi.
Kamu kasih jaga kenapa?
All right, cast iron. Okay, can you see this slide?
Yes.
Yes, Doctor.
All right. Okay, when we talk about cast iron, it is iron plus carbon also, but different category. It is not steel. Okay, so the learning outcome from this module is you should be able to name and differentiate the four cast iron types and the microstructure. You should be able to sketch microstructure of the different types of cast iron and describe the mechanical characteristic and application of different types of cast iron. Okay. All right. When we talk about metal as in the form of alloy, we have two main category. Either it is besi or bukan besi. Either it is ferrous or non-ferrous alloy. Okay. So, but the category for the steel, for the ferrous alloy, we divide it into steel and cast iron. Okay. Steel means the carbon content less than 2%. And it should be able to form 100% austenite. Okay, 100% austenite. Okay, the 100% austenite. Okay, upon heat treatment process, but not cast iron. Okay, but non-ferrous, there are so many. We have copper alloy, aluminum alloy, other alloys such as magnesium, titanium, and nickel. Okay. So for the steel, okay, in fact, we have plain carbon steel and alloy steel. Okay, if it is iron and carbon only, means we call it plain carbon steel. Okay, it's only contain iron and carbon. But this one, iron, carbon, plus, nickel, aluminum, and so many alloying elements. Okay, so now we talk about this only, the cast iron, right? Cast iron, as their name implies, are intended to be cast, okay, into any desired shape instead of being cold or hot work, okay, to shape it, okay. For the steel, yes, we have the roll shape, okay, whether it is a plate, it is it is a rod, it is a bar, whatever, and then only after that we shape it into a final product. Okay, by using rolling process, fogging process, drawing process, bending process. So basically the shape is not really complex. You cannot have a very complex shape for the steel, okay, unless you do the cutting process, machining process, so many shaping process, okay, which is fall under category of cold working or hot working, okay. So, but if you have cast iron, you just pour into any final shape, such as the what is the example? Engine block. Okay, can you imagine the engine block physical structure? It has so many complex shape. Okay, but we can form the final shape by using casting. We melt the steel, not the steel, the iron carbon metal, and then we pour into the mold. Okay, then we got the product, and then of course we need to do a slight finishing process. Okay, so this kind of ferrous or alloy, or what we call it, metal, the carbon inside the iron is between 2 and 4. Okay, and we add another element known as silicon, which is between 1 until 3%. Okay, other element also may present, but it is not like a alloy steel. Okay, alloy steel is more complex, but this one is minimum. Okay, so this is again, remember this. Okay, remember this. The 2%. Okay, below 2%, we have steel. Okay, the cast iron is beyond that. Okay, the melting temperature is less compared to the steel. Steel melting temperature is high. Okay, so possible if you want to melt it and pour in the mold. Okay, and for the steel, you need to obtain this for a modification, the austenite region. Okay, 100% austenite. You don't obtain it for the cast iron. All right, steel has a polyolithic, which is for eutectic base microstructure, and cast iron has ladyburitic or eutectic, okay, base microstructure. Where here, this is eutectic point, okay, eutectic point. This one is eutectic point. This is eutectic. This is eutectic. Okay, for cast iron, they have this. So they have this microstructure. Okay, when you click down here, you have eutectic structure of the cast iron. Okay. So the eutectic composition is at 4.3% here. Okay. Still initial crystal as complete solid solution is austenite. Okay, but okay, this one I have explained just now. So the main category of cast iron, we have white cast iron and gray cast iron, and ductile cast iron and malleable cast iron. Okay, and then for the white cast iron is actually if you have a carbon between 1.8 to 3.6 and low carbon, low silicon. Okay, remember for the cast iron, it has between 1 until 3% silicon. But if it is low silicon content, we are having the white cast iron. White cast iron solidify in rapid cooling rate, and carbon will precipitate as cementite. Okay, cementite also due to the low silicon content. So similar to the steel, we have cementite. Okay, for the white cast iron. It received its namesake for its white fracture surface color will result from the cementite. Okay. So this is the phase transformation during the casting process. Okay, it's from the dendritic structure of alloy, and then we call it the first phase of austenite form in the liquid. Okay, in the liquid, we obtain the prototype austenite. Okay, this is austenite. This is liquid plus austenite. Prototype austenite because it's going to have another austenite. In the cemented structure here, there are another austenite. The second austenite form after passing through this. Okay, which is in the lamellar structure. Okay, so the first austenite we call it proeutectic austenite, and then we obtain the eutectic austenite when it's passing through this eutectic line. Okay, so this called the Lederberg structure, and then ferrite plus cementite forming in the lamellar structure. Okay, so we call this mixture as the Lederberg 2. So the microstructure of as-cast white cast iron contain large amount of iron carbides in eutectic matrix. Okay, this is white cast iron. It is hard and brittle. Okay, so former proeutectic austenite and ferrite at room temperature. Okay, former eutectic austenite ferrite at room temperature. So this is eutectic cementite. Okay, this is formed after passing through the eutectic line. So what cast iron are used in abrasion? Why? Because it is hard. Okay, abrasion resistant part because of high hardness. So this is the application. Where the brittleness of the minimum concern. Okay, of course, when we talk about hard, it is always brittleness. But for this kind of application, if brittleness is not a main concern, we can use this white cast iron. Okay, for example, ball miller. The liner for cement mixer of the ball miller. Okay, so this is the part where it's okay for the structure to have brittleness, but the hardness is a main concern. Okay, the structure also very thick, so the brittleness will not dominant from the application. Okay, in cast iron, the richer carbon content facilitate graphite precipitation. Okay, so the graphite, the carbon will form one structure called graphite. Okay, also addition of high content of silicon will stabilize the carbon in the form of graphite as opposed to cementite. Okay, so we add silicon more. Okay, unlike white cast iron, we can have because white cast iron have the cementite. Okay, cementite for white cast iron. But if we add silicon, we can have graphite, the carbon in the form of graphite. Okay, so that's evolved the formation, the grade of cast iron itself by producing gray cast iron. Gray cast iron contain between 2.5 and 4% carbon. Okay, this gray cast iron is formed when the carbon in the alloy exceed the amount or that can dissolve in the austenite and precipitate as graphite flakes. Okay, it does not form cementite. Instead, it forms graphite. Okay, when a piece of solidified gray iron is fractured, the fractured surface appear gray compared to white cast iron because of the graphite, no cementite. Okay, white cast iron we have cementite. Okay, but gray, we add more silicon because of higher silicon content. The carbon will form graphite instead of cementite. Okay, the solidification. Oh, sorry. Okay, we have proetectoid, austenite. Okay, and then austenite graphite in the eutetic line, eutetic temperature. Okay, we still have austenite, but this austenite forms in the form of eutetic. Okay, and then the proetected cementite and eutectocolite. Okay, eutectocolite. For the graphite itself, it's already formed at this stage. Okay, you can see this black dot remain in the microstructure. Okay, this black dot, all this black dot, it is a graphite. And then after passing through this line, oops. Okay, after passing through this line, you can get eutectocolite. Of course, below this line, you get eutectocolite. Okay. So the microstructure of gray cast iron contain graphite flakes. Okay, it's formed after the what we call eutetic line. Okay, and the moderate cooling rate from pyrrolitic gray cast iron, and slow cooling rate from ferritic gray cast iron. Okay, this is graphite flakes. Why it called flakes? Because imagine cornflakes. Okay, let's say in your cake there is a cornflakes, and when you cut your cake, you can see a shape like this at the cross section. So it is actually a structure of flakes. Okay, of flakes. So the flakes itself is a graphite that forming after eutectic reaction. Okay, after you passing through this temperature, you can get these flakes. Okay, slow and fast cooling will determine the different types of this one. Okay, this after this reaction, okay, this temperature, if you conduct fast cooling, you can get eutectic microstructure, but slow cooling will get ferritic microstructure because the carbon tend to diffuse into forming the graphite during the slow cooling. Okay. All right. Application of gray cast iron. Okay, gray cast iron. Compared to the white cast iron, the gray cast iron has higher strength. Okay, strength is opposed to the hard. Okay, it is always associated with high. The strength is always associated with hardness. Tetapi when we talk about strength, means it has some amount of ductility. Okay, especially in the compression, and it has higher melting temperature. It's very resistant to wear and has excellent vibration damping. Okay, because less brittleness. Okay, if you have less brittle compared to the white cast iron, you can do for the vibrational damping material. Whatever the structure that experience vibration, this structure can be sustain the resist to the damage caused by the vibration. Okay, for example, engine cylinder block made of gray cast iron, which has an excellent damping absorption. Okay, the composition of that cast iron is similar to the gray cast iron. Okay, meaning that you, if you have gray cast iron, you can modify it to become a ductile cast iron. Okay, so of course, you need to know what is the carbon content for the gray cast iron, and what is the silicon content of the gray cast iron. Okay, this is gray cast iron. Okay, by adding a small amount of magnesium or cerium or both, okay, to the grey cast iron before casting, you can have this ductile. How the ductile properties is obtained? Okay, it is still you can get graphite because of the cast iron, because of the silicon, because of the chemical composition that you choose for your alloy, for your cast iron. So there are still graphite, but we actually by adding this magnesium and cerium, we actually modify the shape of the graphite. Okay, so the shape is nodule or spherical, a sphere-like particle. So you have done your lab 1, right? In the material science lab. So can you see the difference in terms of the graphite shape?
Yeah.
Yes, okay. So the black microstructure under microscope image, you can see clearly the flex and the spherical shape. So in ductile iron, graphite is in the form of nodules, okay, bulat sphere, rather than flex, okay. So but if you conduct different cooling rate during the casting process, you will have a different best microstructure. Either it is a pelagic or lamellar structure, or this one, like this one, this is graphite, okay, and then this is the lamellar structure, pelagic, okay. Uh, if you have a slow cooling rate, you will get ferritic ductile cast iron. Okay, it has good fluidability, castability, excellent machinability, and good wear resistance. It has properties similar to the steel, such as high strength, toughness, and ductility. Okay, so ductile iron part is a part made of ductile cast iron, commonly used for drinking water transmission. Okay, malleable cast iron is the first part of cast iron. Okay, it is uh, its carbon and silicon content is varied, which is between 2.6 carbon, and for the silicon is 1.1 until 1.6%. Okay, this one to improve what cast iron. Okay, what cast iron, which is by heat treatment. Okay, basically you have what cast iron. It is brittle. Okay, let's say this is a composition that you want, which is a white cast iron, but you just want to improve. You want to eliminate the brittleness properties. Okay, by improving the ductility. So you can modify the microstructure. Okay. So initially you got a white cast iron. You heat it in the furnace. Okay. What happened is this dissociated iron carbon of the white cast iron and forming a graphite, okay, instead of cementite. The graphite is malleable cast iron. In malleable cast iron is in the form of irregular nodular aggregates called rosette. Okay, so it is not it is it is not nodule, but it's a equate shape, meaning that it's a three-dimensional shape. Okay, like sphere, of course, it's circular in the cross section, but rosette is a irregular shape. But it is not 2 dimension; it is 3 dimension. So if you have 3 dimension, if you give an impact load to the okay, imagine this is a flex. Okay, if you give load here, it will fractured easily, right? But if it is 3 dimensional, okay, either it is a sphere or irregular shape, if you give a load, it will segregate the load, okay, equally throughout its volume. So that's the reason the ductility properties are obtained, meaning that it is able to absorb energy, okay, from any direction of load. So if you have a flex, if you have this load, the load at this direction, maybe it's okay. But we cannot expect that the flex can be arranged orderly like this. The flex will be distribute inhomogeneously, okay, at any direction. So if you get you are unlucky, give a load at this direction of the flex, so meaning that the brittleness property will dominate at that time. But to make it safe, if you have irregular shape or spherical shape, okay, any direction of load, it can be easily absorbed the load. Okay, so the microstructure of malleable cast iron, okay, like this. It is not spherical, but it is three-dimensional. It is not flex. Okay, so heat treatment of white cast iron causes the decomposition of the cementite. Okay, originally white cast iron having cementite. So we do the heat treatment, we can get graphite, okay, which exists in the form of rosette surrounded by a ferrite or pearlite matrix, okay, depending on the cooling rate. If you do it slowly, you can get ferritic. If you cool it faster, you can get pearlite, okay. So the diffusion of carbon tends to form agglomerate at one point. Carbon will diffuse out from the pearlite structure or whatever the cementite structure. They will form one new territory at one point. So this territory of carbon identified as graphite. Graphite instead of atoms diffuse inside the iron. Okay, they gather together, form a new territory. Okay, so the bonding between the carbon known as graphite. So the application of malleable cast iron has good castability, machinability, strength, toughness, corrosion resistance, and uniformity since all casting are heat treated. Okay, because of the improvement towards the brittleness of the cast iron, which is dominated by the intermetallic compound known as cementite, so we can do this kind of process, okay, which is machinability. If you want to do any machining process, you can do it, okay. So rosette shaped graphite mold made the cast iron ductile. See, look at this application. The shape is quite complex. You can make a thread here, okay, by machining process or co-working process because it is less brittleness. Kalau dia brittle, memang susah you nak buat bentuk-bentuk kompleks macam ni. Alright, so in summary, cast iron contain higher carbon contents than the steel. Okay, carbon content high from the steel. So that's the reason you got graphite. Too many carbon. Okay, they form a new territory. Okay, they form bonding between one another instead of trap inside the iron structure forming the cementite. So that's the reason high carbon content forming graphite, and this is applicable for the cast iron. Okay, and then for cast iron, most of the carbon exists in the graphite form rather than combined with iron to form cementite. Okay, I have explained just now. And grade or ductile, malleable, three most widely used in the cast iron. The latter two are reasonably ductile. Inilah malleable and ductile because of the shape of graphite. Okay. Remember the graphite itself is brittle. Okay, it is just carbon. Bayangkanlah arang kan, arang. Okay, it's a brittle. But if you modify the shape into nodular or whatever 3D irregular, it's improved as compared to the flex. Okay, nipis here, right? Very thin, structure of graphite. So we modify the shape of the graphite, then we can improve the toughness, okay, or the ductility. White cast iron is the only cast iron that retain the carbon in the form of carbide. Iron carbide. No. Cementite. In the cementite. Okay, cementite. right? So if you look at this diagram, okay, this is the summary. All right. If you have white cast iron, okay, white cast iron, you do the heat treatment process. Okay, the heat treatment process, you can have modification of cementite. Okay, this one contains cementite, which is Fe3C. Okay, you modify the cementite. Okay, this is contains cementite into graphite. Okay, if you do fast cooling, you can get palladic matrix. If you do slow cooling, you can get ferritic. But you need to do this heat treatment process. Whatever what cast iron that you obtain, you reheat and hold at that particular temperature for more than 1 day. Okay, 30 plus hours. And then you cool it down, you can have different types of matrix malleable cast iron. Okay, this one is higher strength compared to the other one. Okay, because of the palladic structure. And then if you have gray cast iron, okay, where you can obtain different types of the matrix. Moderate, you can get the palladic matrix. Slow, you can get ferritic matrix. Okay, for this kind of alloy, before you do the casting, okay, if you have this specific carbon and silicon content, you just add another element, okay, which is magnesium and or cerium. Okay, you just add this alloying element, and then you control the cooling rates, whether it is moderate or slow cooling. You can have nodular structure of graphite. Okay, so this is the most ductile cast iron. I think that's all for this topic. We finish this topic because it's very short topic. So any question before we end our class for today?
Doktor, soalan untuk group assignment tu. Kami present and record ke kena just record je, tak perlu present dengan doktor?
Tak perlu present saya, hantar video saja.
Video saja.
Presentation dalam video tu.
Okay.
Okay. So you boleh practice lah. You boleh cut lah mana yang you rasa tak ni. Okay, ada lagi soalan? Tak ada? Kalau tak ada, saya rasa itu saja. Siapa yang belum scan attendance, boleh scan sekarang.
Doktor, video berapa panjang maksimum?
Tak ada limit lah pula, tapi logik-logik lah. Maknanya semua orang take part cukup-cukup, jangan sampai sejam kot. Dan paling pun maximum, I think not too short, but maximum I can say, but I never found until 30 minutes. Maybe around 20 minutes, it's okay. 15 to 20. And the way to explain phase diagram, I can share with you. Just a second.